Good morning. This is Ramya Chandrasekaran and I represent Dynavac. This project is about astronomical mirror coating using magnetron sputtering. This is funded by Air Force Research Laboratory and it is a joint work by Boeing and Dynavac. First, a brief background on the current coating technologies and the need for future upgrades. Then we will walk you through a process where we converted a 3.5-meter astronomical mirror coating system from a filament evaporation to a sputtering process. We'll discuss about the benefits of protected silver, the various coating technologies, challenges and risk factors of using protected silver using sputtering process, and some of the mitigation steps we chose. Finally, we will see some process results of protected silver and coating them on a 3.5-meter mirror. Traditionally, large telescope mirrors have been coated with aluminum. Recently, due to the superior properties, there has been an increased interest in coating these mirrors with silver. However, there are two challenging aspects. One, silver has a poor adhesion to the mirror surface. Number two, its tarnishing properties. Due to these challenges, silver demands a multi-layer coating stack, which in turn demands a coating technology that would enable doing multiple layers. In this presentation, we will discuss the system configuration to deposit a multi-layer silver stack and some of its process results. Dynavac commissioned an aluminum evaporation system to coat a 3.5-meter astronomical mirror at Starfire Optical range in 2009, and it has been operational since then. Due to the recent requirements of the telescope, it needed a silver stack, and hence an upgrade was done on the system to deposit a multi-layer silver coating using sputtering process. The entire upgrade was done on site, and in order to mitigate risk factors, some of the testing was done at R&D labs in Dynavac prior to testing at the Space Force facility. Why protected silver? First, let's talk about the benefits of having a protective layer over any reflective layer, let it be aluminum or silver. Having a protective layer helps with improving the durability of the films, which means that it increases the time between the recoats of the telescope mirrors, thus reducing the cost and the telescope downtime. Now, what are the benefits of having a protected silver over having protected aluminum? It all depends on the application and the wavelength one is interested. As you can see from this plot, protected silver works best in the IR wavelengths, while protected aluminum works best in the UV spectrum. So depending on the application, the right material needs to be chosen. Protected silver, or in general silver, reduces thermal emission of the telescope, especially in the IR wavelength regions, reducing the noise and improving the efficiency. Coating technology. There are various coating technologies available, and the most commonly used technology for telescope mirror systems is evaporation, mainly because it's a single layer coating and aluminum was used primarily. It's very traditional and it's well tested and has been around for a few decades now. It's comparatively less expensive, and because it's aluminum process, the mirrors are usually coated between 12 and 18 months. As we began to move to a protected silver, where it demanded a multi-layer stack, a newer technology is needed, and sputtering is its preferred technology for that purpose. It's a new process for large mirrors, so it comes with higher risk factors. It's relatively expensive process compared to the evaporation processes, and but it does come with its own benefits, like what we saw earlier, that the time between recoats can be extended to 24 to 26 months. Coating telescope mirrors using sputtering is still new and has higher technical and financial challenges. Higher technical risk would involve increased telescope downtime during the system setup and qualification. Establishing facilities and utilities is a concern, especially when when there is an existing aluminum evaporation chamber and that needs to be disposed prior to setting up a sputtering process. Here are some of the mitigation steps we followed in order to expedite the schedule. Offline testing using R&D lab chambers. Wherever possible, we did testing in an independent system, example process development and durability testing of components. System upgrade. An existing aluminum evaporation chamber can be efficiently upgraded to a sputter deposition process, and this would help tremendously with cost, lead time, and facilities. Protected silver. Protected silver stack consists of 4 layers. First, adhesion layer. As we discussed before, silver has a poor adhesion to the substrate. Hence, an adhesion layer, which is a nickel chrome nitride, is added between the silver and the substrate. Then comes the reflector layer, which is the silver, followed by an interlayer, which is again a thin layer of nickel chrome nitride. This creates nucleation sites for producing very dense protective layer. And finally, the protective layer, which is a silicon nitride. This helps with the durability of the films. Now, each and every one of these layers are very crucial, and the thickness is very important because without optimizing the thickness, we cannot achieve the desired reflectance and durability factors. Aluminum evaporation system prior to the upgrade. The system is a bell jar configuration. It has 2 chambers, the top and the bottom. The top chamber can be moved up and down, and the bottom chamber can be translated in and out. During the mirror loading and unloading process, the top chamber moves out, the bottom chamber translates out on the tracks, the mirror gets loaded, and the bottom chamber is moved under the top chamber where it is sealed up for vacuum. Cryopumping system is used in order to reach the high vacuum pressures. Prior to depositing aluminum, the mirror is cleaned using a glow discharge process. This helps with better adhesion of aluminum to the substrate. Dynavac's proprietary filaments wetted with the right amount of aluminum is used for producing a precise coating. The filaments are arranged and fine-tuned to obtain the required uniformity across the mirror. This slide shows what was done in order to upgrade the filament evaporation chamber to a sputtering chamber. We repurposed the chamber, most of the pumping system, control system, installation tracks, and utilities. The most important change was the deposition system itself. We replaced the filament rack with magnetron cathodes. We used appropriate power supplies and process gas. Each deposition source had its own uniformity mask. We upgraded the control system to enable magnetron sputtering. Each cathode has its own shutter, which had to be precise and accurate. And finally, the substrate rotation. In order to achieve uniform deposition, either the mirror or the cathode assembly had to be rotated. And as a simplistic approach, we chose to rotate the mirror. 4 magnetron cathodes were used. Although for protected silver, only 3 cathodes would be used because it uses only 3 material. The 4th cathode was installed just to provide the capability of upgrading the system in case they chose to use a 4 material stack. The cathodes were mounted on a radial beam assembly that was designed to have a positional adjustment in terms of angle, throw distance, and the radial position. This helps with various mirror sizes, primary, secondary, and tertiary, and also it helps with optimizing uniformity. Each of the cathodes were positioned within a gas box, and this helps us with obtaining a very confined plasma with a greater process control. Precise shutter movement is critical for continuous and uniform deposition, especially for chambers like this where the substrate is rotated underneath the cathode. It is very likely to have a strip of non-uniform deposition where the start and stop of the deposition takes place. The best way to eliminate this is to have a very fine shutter movement. Pneumatic shutters were used for each cathode and they were independently controlled. Large reliable shutters are always a design concern in these kind of chambers, mainly because of 2 reasons. One, the shutters tend to get hot and they tend to get accumulated with a lot of sputtered material
because of the burn-in cycles. Hence, a thorough analysis was done in the design phase and experimentally verified during the testing phase. During qualification, we did about 250 open-close cycles in the R&D lab chamber at Dynavac with simulated heat using heat lamps, and we repeated the test in the actual chamber with plasma. A multi-stage pumping system was used. A rough pump helped bring the pressure from atmosphere to a crossover pressure. Cryopumps and Meissner coils were used to achieve lower pressures. The cryopumps were equipped with throttle valve and they helped mainly with process gas pumping. The Meissner coil helped enhance water vapor pumping during the process. The process gas pumping can either be controlled upstream or downstream, and we have used both methods of control during our process.
Process development. Process optimization and development in these large chambers is a critical factor in achieving the desired results. And we needed a setup that is flexible and where we can load in samples that can be characterized easily. We used a Weiffel tree setup, which kind of simulated the curvature of the mirror. It had arms where we can set up crystals or test coupons. And we had multiple crystal sensors that was located in different locations on the simulated mirror. And we could monitor the deposition rate and thickness during the deposition. This helped us from having to vent and pump down the chambers for every small change. And this expedited the process time. And once we got into a fine-tuning mode where we know the regime of process control, we started loading microscopic glass slides. And we, uh, we characterized the films for reflectivity and adhesion, and we optimized the uniformity by tailoring down the uniformity masks. This slide shows experimental results of aluminum and protected silver. And as we can see, protected silver has improved performance in the IR spectrum, and it also avoids the dip at 800 nanometer wavelength. Film quality. The roughness of the films were measured. So prior to putting in any protected silver coating, we measured the substrate roughness, and it was about 4 nanometers. And post-coating, we also measured the roughness, and it was about 5 nanometers. So this kind of tells us that the coating does not increase the roughness drastically, which benefits in obtaining better optical properties.
Effect of silicon nitride and nickel chrome nitride layers. As we discussed earlier, the thickness of these layers are very critical in obtaining the desired results on the optical and durability factors. Silicon nitride layer thickness, we varied it from 85 angstroms to 120 angstroms, and we looked at the reflectivity results, adhesion results, and also we did some environmental testing, basically putting these samples through a high stress test. The conditions were 30 degrees C at a relative humidity of 90% for 2 weeks. And within this thickness regimes, we did not see any adverse effects with silicon nitride thickness. We did the same on the interlayer as well for the silicon nickel chrome nitride layer. This layer is so thin and it's very critical to maintain that thickness because too thick a layer affects reflectivity, too thin a layer affects the durability of the films. Studies have shown that the ideal thickness is 6 angstroms. However, controlling and quantifying that thickness is pretty challenging. Hence, we started off with 6 angstroms and we doubled it approximately to see if there was any noticeable change. And fortunately, we did not see any difference in the optical properties and the adhesion properties, which is a good news. So, which means that there is a range of thickness we could live with, and it will not show up any adverse effects on the reflectance and the adhesion properties. Protected silver environmental test results. So we did environmental test results on our standard set of protected silver coated samples. And we particularly paid attention to the start and stop positions. As we discussed earlier, one of the likely places where non-uniformity could occur is where we start and stop deposition, that strip along the mirror. So we put glass coupons along that strip, and we looked at the reflectance and adhesion, and we also put the samples through stress test. As we can see in the plot, there was a mild change around the visible regime, but they are pretty insignificant considering the noise factors in the measurements. This kind of tells us that the shutters worked precisely well and reasonable enough that we don't see noticeable change along that strip. Low temperature gradient is very crucial to prevent the mirror from cracking. We did a lot of mathematical simulations in order to understand the temperature gradient, and experimentally we confirmed it by using 6-inch square blocks similar to the thickness of the mirror, and we epoxied thermocouples onto it to minimize the noise. These blocks were mounted onto the simulated mirror, and we processed them as we would process the mirror. We looked at the temperatures, and the temperature gradient between the top and bottom surfaces were pretty much negligible. We couldn't see any temperature difference. The temperature difference between the inner and outer radii of the mirror was around 6 degrees C. And this was acceptable with the mirror, and hence we proceeded with coating the mirror with the actual protected silver coating. This is a picture of a coated mirror with protected silver. As you can see, it's a beautiful mirror with a very good reflectivity. We can see the reflection of the coating chamber with the Dynavac logo in it. Optical performance on mirror over time. So we did have witness samples in the telescope, and we measured the reflectance over time. And this plot shows the reflectance data over a period of 18 months. And as we can see here, it stayed put and there was no noticeable change in the degradation over time, which is a good news. Conclusions. An aluminum filament evaporation system was upgraded to a sputter deposition system to deposit multi-layer silver stack. A protected silver coating was successfully applied onto a 3.5-meter telescope mirror. Negligible degradation in optical performance was observed over a period of 18 months on the witness samples placed next to the mirror in the telescope. Thank you.